Every autumn, the Columbia River basin transforms. Tens of thousands of Chinook salmon push upstream, a migration so ancient it shaped the rivers themselves. Fishermen plan their seasons around it. Eagles follow it. Bears depend on it. But in recent years, something has changed. Monitoring stations along the Snake and Salmon rivers began recording numbers that didn't make sense. Fish counts were dropping, not gradually, the way populations naturally fluctuate, but sharply and consistently. In some tributaries, stretches of river that once ran silver with returning fish were nearly empty. Wildlife biologists who had spent decades on these rivers said they hadn't seen anything like it. Not this widespread. Not this sustained. The first instinct was to look upstream, at water temperatures, at spawning grounds, at the gravel beds where salmon lay their eggs. What they found there was concerning. But it wasn't the whole story. Because when a separate research team followed the fish in the other direction, downstream, toward the coast, they discovered something waiting in the estuary that nobody had anticipated. Something that was quietly intercepting salmon before they ever had a chance to return. The mystery wasn't just about why salmon were disappearing. It was about what had changed in the ecosystem below, and how long it had been building without anyone noticing. The Columbia River system is one of the most complex waterways in North America. It stretches across more than 250,000 square miles, pulling snowmelt from the Rockies, carving through basalt plateaus, and eventually spilling into the Pacific Ocean near Astoria, Oregon. For thousands of years, salmon have used this system like a highway. They're born in cold mountain streams, migrate to the ocean, grow for years in open water, and then, following signals scientists still don't fully understand, they return to the exact stream where they hatched. It's one of the most precise navigational feats in the natural world. So when the numbers began dropping, people noticed immediately. Tribal fisheries managers on the Nez Perce Reservation were among the first to formally document the decline. They had been tracking salmon populations for decades, and the data from the mid-2010s onward showed a pattern that was difficult to dismiss. Returns were falling below recovery thresholds. Some runs that had shown signs of stabilizing after earlier conservation efforts were declining again, faster than before. State wildlife agencies confirmed similar trends. Federal monitoring systems flagged the same rivers. The initial investigation focused on the usual suspects. Water temperatures in key spawning tributaries had risen during several consecutive dry summers. Sediment levels in some streams had increased, reducing the oxygen that salmon eggs need to survive. These were known stressors. Manageable ones, researchers believe. But then a biologist working for a university research program out of Portland began analyzing the data differently, not looking at where salmon were dying, but tracking where they were disappearing from. And the pattern pointed somewhere unexpected. Not upstream. The estuary is where the river ends and the ocean begins. For salmon, it's a transition zone, a place where their bodies shift from freshwater to saltwater, where juvenile fish spend weeks adjusting before heading out to sea. It's also where they're most vulnerable. Dr. Marcus Teller, a fisheries ecologist at Oregon State University, had spent years studying salmon mortality in the lower Columbia. Most of his work focused on the juveniles, the smolts making their first journey downstream. What he found in the estuary data stopped him. Survival rates for smolts passing through the lower river had declined significantly over a 10-year period. Not at the dams. Not in the warm mountain tributaries. In the estuary itself. Something in that transition zone was intercepting fish at a rate that the models hadn't predicted. Teller's team set up acoustic tagging stations along the final 60 miles of the Columbia. Tiny transmitters implanted in juvenile salmon would ping receivers as the fish moved downstream. Hundreds of fish entered the lower river. Far fewer signals appeared on the other side. The team reviewed the data repeatedly, looking for equipment failures, tagging errors, anything that might explain the gap. The equipment was working perfectly. The fish were simply vanishing within a specific stretch of the estuary, a zone roughly 12 miles wide, near the river's mouth, where tidal influence and freshwater flow interact in complex ways. And then one of Teller's graduate researchers noticed something in the aerial survey footage they had collected the previous spring. The vegetation along the estuary margins had changed significantly. A particular species of cordgrass, non-native, highly invasive, had expanded its coverage along the mudflat edges by nearly 40% in 5 years. It didn't seem connected at first, but the boundaries of the cordgrass expansion matched almost exactly with the zone where the salmon signals were disappearing. That alignment was too precise to be coincidence. Spartina alterniflora. It's a cordgrass native to the Atlantic coast of North America. Somewhere along the way, likely introduced through shipping ballast or deliberate planting for erosion control decades ago, it established itself in Pacific Northwest estuaries, and it had been spreading quietly ever since. On the surface, cordgrass doesn't look threatening. It's a marsh plant. It stabilizes sediment. In its native range, it plays an important ecological role. But in the Columbia estuary, it was doing something different. Teller's team began working with a botanist from the U.S. Geological Survey named Dr. Colin Marsh, who had been tracking Spartina expansion along the Pacific coast for years. Marsh already knew the plant was a problem. What he didn't know was how deeply it was connected to salmon. As the two research teams combined their data, a picture began forming that neither had expected to see. Native estuary habitats, open mudflats, eelgrass beds, shallow tidal channels, are critical rearing grounds for juvenile salmon. The fish use these areas to feed, to adjust to salt water, to build the energy reserves they'll need for years at sea. The Spartina was replacing those habitats. Dense cordgrass mats were filling in the shallow channels. Mudflats that once hosted the invertebrates salmon feed on were being buried under root systems that altered the sediment chemistry entirely. The fish weren't being eaten in that 12-mile zone. They were arriving in habitat that could no longer support them. Weakened, underfed, physiologically unprepared for the ocean. The ones that made it through were compromised before they ever reached open water. But then Marsh pulled up satellite imagery from 15 years earlier, and what he saw made the situation considerably worse. The Spartina hadn't started in the Columbia estuary. It had started much further north, and it was still moving. The satellite imagery told a story that no ground-level survey had fully captured. Spartina had first appeared in significant concentrations in Willapa Bay, Washington, one of the most productive estuaries on the Pacific coast, sometime in the late 1980s. By the early 2000s, it had colonized thousands of acres of mudflat there. Willapa Bay also happens to be a critical rearing ground for juvenile salmon from multiple river systems. The timing aligned with something researchers had noticed but never fully explained: a gradual decline in early ocean survival rates for Columbia and Chehalis River salmon that began in roughly the same period. Nobody had connected the two things. Until now. Marsh overlaid the Spartina expansion maps with salmon survival data going back 3 decades. The correlation wasn't perfect. Ecosystems never produce perfect correlations, but it was consistent enough to demand serious attention. Every major estuary where Spartina had established dense coverage showed a corresponding dip in juvenile salmon survival rates within 5 to 8 years of colonization. 5 to 8 years. That was the lag time between habitat loss and population impact, long enough that by the time the decline became visible in adult return counts, the cause was already years in the past. This was why nobody had found it sooner. They were looking at consequences while the cause kept moving. And Marsh's current mapping data showed Spartina actively expanding into Grays Harbor, into the Nisqually Delta, into smaller estuaries along the Washington and Oregon coasts that hadn't yet shown significant salmon decline. But they would. Teller sat with that information for a long moment, because there was one more detail in the data that neither team had discussed publicly yet. Control efforts for Spartina, herbicide treatments, mechanical removal, had been underway in Willapa Bay for years. They had slowed the spread. But in the Columbia estuary, no coordinated removal program existed, and the cordgrass was still growing. The findings were published in late 2023. The response from the scientific community was immediate and uncomfortable. Not because the research was disputed, but because of what it implied about decades of salmon recovery efforts. Billions of dollars had been spent on upstream interventions, fish ladders, dam modifications, hatchery programs, riparian restoration along mountain tributaries. All of it necessary, all of it valuable, but none of it accounted for what was happening at the other end of the journey. A salmon that successfully navigates a fish ladder, survives warm water temperatures, hatches in clean gravel, and makes it 300 miles downstream can still be lost in the final 12 miles, in habitats so altered it can no longer perform its most basic function. That realization landed hard in the conservation community. Teller described it as finding a hole in a bucket that everyone had assumed was intact. Emergency assessment surveys were launched across 6 Pacific Coast estuaries in 2024. Federal agencies began coordinating with state wildlife programs to map Spartina coverage at a resolution that hadn't previously existed. What those surveys found in Grays Harbor was worse than projected. Cordgrass coverage had increased by nearly 60% in 3 years, faster than the models had predicted, likely accelerated by shifting sediment patterns from upstream flow changes. A removal program was fast-tracked. Funding was approved. Teams were deployed. But here is what the researchers were careful to say publicly. Spartina, once established at scale, does not disappear quickly. Even aggressive removal efforts in Willapa Bay had taken 15 years to show measurable habitat recovery. 15 years. For salmon populations already below recovery thresholds, that timeline is not a comfortable one. The rivers can be protected. The spawning grounds can be restored. The fish can be given every possible advantage upstream. But if the estuary isn't there waiting for them, healthy, functional, intact, the journey ends the same way regardless. Quietly, out of sight. 12 miles from the ocean. The salmon were never just a river story. They were always an estuary story too. We just weren't watching the right part of the river.